All right, line A1, learning task 7, we're going to talk about principles of electromagnetic induction. We're going to have to go back to a couple of other left-hand rules that we're going to learn, as well as some new ones. But we're first going to just talk about what exactly electromagnetic induction is. Back in the 1800s, when electricity was still a bit of a curiosity, but people were starting to see its commercial possibilities, Michael Faraday was experimenting with it. And he noticed that whenever you would move a conductor by a magnetic field, you'd be able to go and generate a little bit of voltage off of that. And so he did a bunch of experimentation and, kept track of what was happening and when, and eventually he put this all together into a law. And the law is what we refer to at this point as Faraday's law of electromagnetic induction. It's a law. It means it's always going to go and happen whenever we have got the stuff that's inside of it, or inside of this law in place. Namely, if we have got turns of wire, if we've got some magnetic flux, and if we've got some movement, we're going to go and get voltage. And his law was that the magnitude of voltage, the size of the voltage, induced in a turn of wire is proportional to the rate of change of flux passing through or linked with that turn. This sounds a little bit confusing when we write it out like that, and so what we had is later on it got put down into a formula, and this formula is going to be inside of your formula sheet that you will see from ITA, and it's going to be EG, or the generated value of voltage, sometimes just a small e, other times it's going to be the EG, is equal to my BLV. The B over here is the Greek letter beta, and it's going to be flux density in Teslas. So not the actual number of lines of flux, but it's the number of lines of flux per square area that we're going to go and have. L is going to be my conductor active length. Now, active length means it's the amount of conductor that is inside of the field. And it's going to be measured inside of meters. And velocity is going to be the relative velocity of the conductor at right angles to the magnetic field in meters per second. What this means is if we know what our size of our magnetic field is, let's go and say that we've got a north over here, we've got a south over there, and that we've got magnetic lines of flux. We'll just go and stick a metal keeper across here, like that. What we'll have is coming out of this north pole, we're going to go have magnetic lines of flux that are going to go and pass through this piece of ferrous iron and form complete loops. This is basic magnetic theory that you would have covered in first year. Okay, so we have all of these lines of flux that are going to be passing through there. If we take a conductor and then we pass that conductor through there, the active length of the conductor is going to be the chunk of conductor that's actually inside of that field. This conductor itself could be super, super long. Like if I were to go and draw it from the side, I might have, this conductor over here, and then I might have, a whole big loop of it. The only part that is going to be active is going to be this part that is going to be passing through the field itself. So when we're talking about the length, we're not talking about the overall length, we're talking about the active length, or the amount that's going to be inside of the field. Once it leaves the field, it's no longer active. And then velocity is just going to be how quickly I put it through there. If I take a look at this formula, I see that everything inside of here is a direct relationship to my amount of voltage. In other words, if I were to go and increase the flux density, I'm going to go and see an increase in my value of voltage. Or if I were to increase the active length, stick more turns of wire inside of the magnetic field, I'll see an increase in voltage. Or if I were to go and move the wire faster through the field, or the field over top of the wire, whatever one I'm moving, then I'm going to go and have, once again, a increase in the amount of generated value of voltage. So I can go and change my voltage by changing any one of these three that we are going to go and have. Active length is usually going to be increased by taking my conductor and then coiling it. Instead of having just one chunk of conductor going through the way that we see on this picture over here, what I'll do is I'll take that conductor and then I will pass it through here again. And then I can go and pass it through here again. And now all of a sudden I see that I've tripled my amount of active length by adding this thing into coils. Flux density is normally going to be controlled by electromagnets. I drew a permanent magnet inside of here, but you would have covered it back in first year electromagnetism. The fact that you can go and create an electromagnet by taking any type of a iron device. We'll just take an iron device over here. And then I can go and wrap coils of wire around it. Put a bunch of wraps, and then I can go and put current through it, and as soon as I put current through it, DC current is going to go and create a magnetic field. If I would go and increase the amount of current, I'm going to go and see an increase in the magnetic field. If I would decrease the amount of current, I'm going to go and see a decrease in the amount of current. And this is all going to be measured in Webers, which are going to be equal to my amperes times my turns, right? More amps is going to go and give me more Webers of flux. That's the number of flux lines. The number of flux lines, when they get up to here, those flux lines are going to go and do a little bit of fringing, where they bulge out as they go through there, which is going to decrease the flux density, right? They're less dense because they're bulged out a little bit, but I'm still going to go and have, a decent amount of Teslas that I'm going to go and have. Teslas is just going to be the measurement of the number of lines of flux over top of the area. So we have lots of lines of flux generated, our Webers through our ampere turns, but then they're going to go and spread out, which means that my Tesla value is going to be a little bit decreased as a result. We usually go and control all of this by just putting something in line with this. And usually it's going to be something like a rheostat, which is a variable type of resistance, so that I can adjust the amount of current that is going to be traveling through this coil, which would then adjust my amount of amps over here, which would then adjust my amount of Webers, which would then adjust my amount of flux, my flux density, my Teslas over here, which would adjust my amount of voltage. Anytime that I change my velocity of whatever I'm going to be moving it through here with, and usually what we're going to do is we're going to move it through in a circular motion around and around and around and around again. It's going to go and change my frequency as well as it's going to change my voltage. We'll look at the frequency later on. For now, we'll just take a look at the voltage. If we increase the velocity that we move through there, we will increase our value of voltage. This is all done through the use of what is referred to as a prime mover. A prime mover is going to be the thing that drives our alternator, which is our way that we create AC. It could be our water turbines inside of dams, it could be generators, it can be windmills, all sorts of different things that could be powering that. This was Faraday's law, this one over here. We're going to go and use this one a load throughout this year as well as through third year. It's going to be probably one of your most memorized formulas or most widely used formulas throughout all of second and third year. The other one that we're going to take a look at is Lenz's law. And Lenz's law is simply just going to be a repetition of Newton's third law, which that for every action, there must be an equal and opposite reaction. And Lenz's law states that the direction of the induced EMF, so the generated value of voltage, the direction or the polarity of the induced voltage must be such so that any current resulting from it will develop a flux that will oppose any change in the original flux. In other words, it's going to develop another type of voltage called a counter EMF. That's what we're going to be looking at inside of here. What we will find is that as we change the current value going through a conductor, that current value is going to change the flux lines around that conductor, which are going to cut through themselves to that conductor itself, which is going to generate a back voltage pushing back around it. Once again, let's cover that once we actually get into that inside our next learning task. For now, just note that we are going to go and have an induced voltage, but then we're also going to go and have a counter EMF or a slowing effect that is also going to be created. Okay, let's talk about left-hand rules. You did learn two other left-hand rules back in first year. We are going to use these at times throughout this year, so let's just cover them all, and then we'll get into the new one that we're going to learn. So this is review. First of all, the left-hand rule for conductors. That's going to be this first one over here. And that's if I know the direction of current. In other words, if this is negative and this is positive and my current is traveling through in that direction, if I stick my thumb in the direction of current, and if I curl my fingers around, the curling of my fingers is going to go and tell me the direction of the rotating magnetic field, the flux field that is going to be generated from that. Okay, that's the left-hand rule for conductors. Practice it once or twice until you're comfortable with it. The other one that we have is our left-hand rule for coils. And the left-hand rule for coils states that now I'm going to go and curl my fingers around a coil in the direction that the current is going through it. So over here we see got current traveling from my negative, leaves. By the way, anytime that we're looking at a load, current travels from negative to positive through a load, and then travels from positive to negative through a source. So let's go, this is a load, it's a wire, our current is going to travel down and through, and then it travels through that coil, up and around, travels down through that coil, up and around, travels down through that coil. And so what I'll do is I'll curl my left-hand fingers around the coil in the same direction that that current is traveling around that coil. And then the direction that my thumb is is going to go and show me where the north pole of that coil is. This coil over here would have magnetic lines of flux that would be emanating here from the north and transferring all the way back into the south and then traveling back up through there. Remember, magnetic lines form complete loops. They're elastic, and they are going to go and form those complete loops. Our current travels through the rest of this coil. Current travels then back up, hits our battery, and then the electrochemical reaction pushes it back through the battery, and it comes out the other side of this thing. So current flows from negative to positive through a load, and from positive to negative through a source. This is all second year review. You're probably bored. You remember this all. Let's talk about something new. The new thing that we're going to talk about is called Fleming's left-hand rule. And Fleming's left-hand rule is going to go and be a way that we can now relate the directions of multiple things happening inside of our circuit. First of all, it is the left-hand rule for generation. In other words, we are always using this thing to go and figure out how or what direction of current we're going to go and make. Since we're using it to figure it out, that should be the very last thing that we are going to go and look at. So right now, we're just going to go and ignore the middle finger. We will always start with the finger gun, okay? Index and thumb. That's what we're going to start with. Once we have got those two aligned with our circuit components, then we're going to go and unfold the middle finger, and then that's going to go and tell us our direction of current. But because this is what we're using it to look for, we don't start with this. This is what we should end up with. We always start with these two, get these two aligned, then we'll worry about the middle finger. Okay, it's got three main things. First of all, we got thumb. The thumb is going to go in the direction of thrust on the conductor. So TH for thumb, TH for thrust. First finger is going to be going in the direction of the fields, going from north to south that we are going to go and have. And then the center finger is going to be going in the direction of current that we are going to have, or they say middle finger in the movement of electrons. Either one works, whichever works for you. I prefer center finger in the direction of current. But that's what we are going to go and have. In other words, if I have a field that's going through from there, here's my north, here's my south, so I just follow those arrows. If I know my direction of thrust, then it's going to go and tell me my direction of current. This one over here is the left-hand rule as well. It's just the left-hand rule now seen facing towards us, so we might use that drawing there in a little bit inside some of our other stuff as well. Okay, get those values done. If you have trouble mixing up your left and your right hand, and I guarantee you that some of you are going to go and screw a question or two up just because you're using the right hand. Most of us are going to be right hand dominant, which means that you tend to just automatically do stuff with your right hand. Make sure that you are using that left hand. Right hand is going to be for motors. Left hand is going to go and be for inductors. If it helps, just take a Sharpie and write a big L on your left hand for the time being. You're all living at home anyways. Nobody can see anybody. So you might as well, and that way you're at least guaranteed you're not going to screw it up. But make sure it's the left hand, and start with that center finger folded in, because it is the thing that we are looking for, and we have to establish these two first. After that, they go into a couple of examples. Examples 1, 2, and 3. Those examples are all going to be worked off of the EG is equal to BLV. And really what they're going to be doing is they're going to be reworking that formula and isolating for different variables. In the very first one, they're going to go and look at what value of voltage I'm going to go and generate, based upon a conductor active length that's got a field, that's got a flux density in Teslas, and a velocity. And it's going to go and generate a value of voltage. That's straightforward enough. The second one over there is where they are going to go and say, well, we're going to keep the same length of conductor, we're going to keep the same flux density, but now we want to speed up our movement through it so that we can go and produce 347 volts. And so then they go through the reworking of that one. Example number 3 goes and talks talks about now keeping it at that same value of speed that they just moved it up to, but now dropping the amount of flux, the amount of current that we are going to go and have to those field poles, to go and drop the amount of voltage that we are going to have. Work through each of those. Just take the pause, work through each of those, work through your self-test questions, then move on and into your next video.